Hello, calculus student. This video is for chapter 4.4, mean value theorem. The mean value theorem is a very important theorem that leads us eventually prove the fundamental theorem of calculus, so it's worth to spend some time to go over them. You might not need to know the proof. We'll go over the proof a little bit, but you need to know what it means. When would the mean value theorem apply? Okay, so to begin with, just spend some time to prove it. The first proof is to prove something called Rolle's theorem, and then we'll prove the mean value theorem using the Rolle's theorem. Now, the Rolle's theorem can be proved by looking at the book. Okay, so I'm going to switch off and then look at this. So this say that was the Rolle's theorem. Rolle's theorem say that if I have a function such that at the two endpoint is continuous in the closed interval AB and is differentiable inside the open interval AB such that f of A is equal to f of B. That means if you look at the two endpoint, their function value y are the same. Then we say that there is a C such that f prime of C equal to 0. That means it must turn. It must turn. You cannot have two endpoints as the same and it doesn't turn. So theoretically, you can just look at it this way. You say, well, unless the whole things is a constant function, in that case, f prime of C is equal to 0 for the whole interval. If not, there must be some number that is lower than or higher than the endpoint. So this is the case when there is another number that is higher than k, and this number has to be interior to AB. And then because this is a closed interval and also differentiable by the extreme value theorem, we say that there must be an absolute maximum. There must be an absolute maximum, and this absolute maximum will have f prime of C equal to 0. The other case would be if you have the two endpoints equal to k, the same number, and then there is a next value that is lower than this k, then again there is another value that is the local minimum, and this local minimum must turns, and the f prime of C is equal to 0. So in the third case would be if they have both a maximum and a minimum, and in both cases you would have more than one C such that f prime of C is equal to 0. So all these cases you can draw it a picture. Basically the first case is when you have a constant function, so f of A and f of C are just constant function. Of course f prime of C is equal for anything, is equal to 0 for C inside AB, right? And then the second case is when you have the case where this f of A and f of B are the same, and then this is another point that is higher than it, so there must be a C. So this is C such that f prime of C is equal to 0. It has to turn to come back. And then the last one is when there is one that is lower than your K, so this is K, right? Where f of A and f of B is. So there's another number that's lower than it, and it turns out that there would be a absolute minimum because of the extreme value theorem. So that is a C that is the absolute value. So all cases, in all three cases, it shows us that if these two conditions meet, that means f is a continuous function over closed interval and differentiable over the open interval, there must be a C inside such that it turns. You cannot have something that's continuous and then come back but not turn, right? So basically, in a common sense, that's what it says. And then let's look at the mean value theorem. The mean value theorem releases the requirement for the Rolle theorems that say f of A is equal to f of B. It just says that if f is a continuous function over a interval AB and is also differentiable over AB, then there must be a C such that f of C is equal to the slope of the secant line plotted between A and B, because there is a point A, f of A, and a point B, f of B. So basically this is the slope between them. y2 minus y1 over x2 minus x1. And we guarantee that there is a c that would have that slope. It's exactly like that slope. So to prove that, so let's just write the equation that connect the 2 points, meaning that it would pass through A and f of A, and with this slope. So using point slope form, we say our point is this and our slope is this. So the equation would be y is equal to f of A, y2 minus y1, we move it over, plus f of B minus f of A over B minus A times x minus A, right? y2 minus y1 equal to m, this is m, x minus x1, x minus x1. So then we'll define a function, a new function. This function is g of x and is equal to our original f of x minus this line, so minus f of A plus f of B minus f of A over B minus A, x minus A. Is really long, but it's still a function. You plug in x, it will get you something. But this function is very strange. If you plug in A, what happened? Plug in A, all this set goes away. So you have f of A minus f of A. Oh, it's equal to 0. And if you plug in g of B, what happened? Then you have f of B minus f of A plus, so this would be B minus A. You cancel this too because it's B minus A, it's B minus A. And you have another f of B minus f of A. So f of B minus f of A plus f of B minus A. And then this is B minus A, is B minus A. And so, okay, so this is a minus, so this should be a minus. Okay. So this 2 minus this 2 would be 0. I was worrying that y is not 0. So because I did not distribute the minus. So you can see that this particular function are the same. That means g of A equal to g of B. And it satisfies the Rolle's theorem. The Rolle's theorem said that, oh, this function must have a turning point at C by the Rolle's theorem, right? So that means if I do F, there must be a C in AB such that G prime of C is equal to 0. It must turn. So, but what is G prime of C? G prime of C is doing the prime of these. So that would equal to F prime of C. When you do the derivative, this goes away. And then this would just be this term, right? Minus f of B minus f of A over B minus A times 1, right? And it is equal to 0. So that means you should have a point in the function in the interval AB such that f prime of C equal to f of B minus f of A over B minus A. So we proved the mean value theorem. Okay, it's rather strange. If you don't understand it, it's fine. But I just want to prove it. Okay, so the important thing you need to know is first understand when it applies. Okay, when does it apply? The mean value theorem say that it applies if f is a continuous function over a closed interval and differentiable over the open interval. There would be a point C, at least one point C, such that the derivative of you plug in the derivative of it, that means the slope of the tangent line at that point is equal to the second line slope between AB. So let's try to verify it. So maybe after you verify it, you know what we're talking about. So we have a function y equal to 2x cubed minus 9x squared minus 108x plus 8, and this is interval negative 4, 10. Now, so how do we know that it's verified, the mean value theorem? So this is 2 different points. So let's look at the slope between negative 4, f of negative 4. So this is a point 4 and f of negative 4. And the point 10, f of negative 10, right? So we want to find that slope. So we write m equal to f of 10, not negative 10, it's positive 10, minus f of negative 4. It's just 2 points on the graph. And 10 minus negative 4. What would this number be? Oh gosh, it's such a big number. So I'm going to use the decimal to do it. 2x cubed. 2x cubed minus 90 squared minus 108x plus 8. And we want f of 10 minus f of, so we just say m equal to f of 10 minus f of negative 4. It's very easy to do if you have decimal. Divided by 10 minus 4. 10 minus negative 4. So just do the slope formula. Oh gosh. It should be inside here. 10 minus negative 4. Oh, they calculate for us is negative 10. So this slope is negative 10. So what the mean value theorem guarantee is, of course, this is a smooth function, it's continuous, it's a closed interval, that there must be a c such that the slope of the tangent line must be equal to negative 10. There must be a c, the slope of the tangent line. So let's do an f prime of c, x. Part of x, we'll just do the derivative. So that would be 6x squared minus 18x minus 108, right? Mean value theorem said that there must be f prime of c, at least one, that is equal to negative 10. 6c squared minus 10c minus 108 equal to negative 10. So this must be able to solve. So let's move this over. So that would be 6c squared minus 10c divided plus 10. That would be minus 98 equal to 0. Can I factor it? Is it factorable? We can actually use this to do. Let's say g of x equal to 6c squared minus 10c minus 98. Is it solvable? The green one? Oh, it is negative 3 and 4.96. So the what is it? Negative 3.2 and positive 4.96. So there's two number actually. C is equal to 4.96 and also C is equal to negative 3.29. Both of this is within 4, negative 4 and 10. So these C1 and C2, they are inside the open interval negative 4, 10. So MVT apply. That's what you want to do to verify. You verify that when you solve f prime of c equal to this slope, you must have a solution. And this solution must be in this interval. Okay, so I'm going to do another video for the rest of the example.